With this lecture, we begin our next unit for Conceptual Physics AB. This unit covers work and energy. We first of all begin with a mathematical definition, specifically the physical quantity called work. So let's go ahead and define now what is meant by work. The simplest description of this new physical quantity called work, it's usually described as force times distance. However, for our purposes, mathematically, there are actually three different ways to think of it. What I'm skipping around here is a specific type of multiplication associated with vectors. It's called the dot product. Okay, for our purposes, however, only three situations are important. The first situation is if the force vector, I'm going to call it F like so, and the displacement vector, which is usually referred to as delta R, like so, are pointing in the same direction. If the force vector and the displacement vector are pointing in the same direction, then the definition of work is just simply written as force times distance. The work is equal to the force vector multiplied by the displacement vector. So, for example, if I take my air track card here on my air track, and I don't even need the air on in order to describe this, when I do this like so, I do a certain amount of work. The work that I do is equal to the multiplication of the force vector that I apply horizontally to the right-hand side and the displacement vector, delta R, to the right-hand side. That's the first way in which we can consider work. However, we could also consider a situation where the force vector is in the opposite direction of the displacement vector. So in this simple demonstration, don't consider the force that I now apply to the object. Instead, consider the force of friction is acting upon the object when I do this. When I displace the object to the right-hand side, the force of kinetic friction opposes that motion and points in this direction like so. The force of friction is in the opposite direction of the displacement vector. When this occurs, the dot product, the mathematics that I'm skipping over here, gives us the value of work as a negative number. So in this case, the work is equal to the negative of the force multiplied by the distance. In this case, the force vector points in the opposite direction of the displacement vector. And then the third situation to consider is in this horizontal situation, either the normal force, which points straight upwards, or the force of gravity, which points straight downwards. In either of those two cases, the force vector is perpendicular to the displacement vector. When the force vector is perpendicular to the displacement vector, the mathematics of the dot product that I'm skipping over gives us a value of 0 when we multiply the two vectors together. So let me just draw that out here as a simple diagram. What happens if the force vector points in the opposite, or perpendicular to the displacement vector? In this case, the work done by the force is equal to 0. So these are the only three mathematical scenarios that we have to look at when calculating work. The first scenario is that it's simply force times distance when the two vectors point in the same direction. If the two vectors point in the opposite direction, there's a negative sign. And if the two vectors are perpendicular, this then means that the work done by that force is equal to 0. Okay, now this is a new quantity for our purposes here, so let's just go ahead and check the unit. So I'm going to do some erasing here at this point. Like so. And now just using this basic definition here of work as force times distance, let's go ahead and check the units. Okay, so the units are as follows. We have force, if you recall, in metric SI units as newtons. And then we're multiplying it here by distance in terms of meters. A Newton meter is given its own name. It's referred to as a joule. It is named after somebody. And it's spelled in the following manner. Okay, and now what we do at this point is we just calculate or practice calculating the work done by various forces for a simple horizontal situation, much like I have set up here with my air track. So I have this situation set up as a problem for us. I'm going to have it on my screen in just a few moments. I'll read it to you. I'll have you copy it into your notes as we go. Okay, before I do, however, let me go ahead and do some erasing here. Like so. Okay, so the problem is as follows. Okay, so an object of mass 2 kilograms is initially at rest. The object is pulled horizontally across the floor with a constant force of 15 newtons. A force of friction equal to 1/4 of the object's weight opposes the motion. The object is pulled over a distance of 10 meters. We're going to calculate the work done by the individual forces, and we're going to also calculate what is referred to as the net work done. So here's a simple drawing of this situation. All right, so we have this surface like so. Here's our object of mass m. We're given that the mass of the object is 2 kilograms. Okay, the object is initially at rest. Okay, and then I come along and I exert a force like so horizontally. We're going to call this force here F pull. This is what is given to me numerically as 15 newtons. Okay, and then opposing the motion like so is going to be a force of friction. The force of friction is given to us as 1/4 of the object's weight. Recall from the previous unit that the weight is equal to the force of gravity exerted upon a mass. It's equal to m multiplied by g, acceleration due to gravity. Okay, now we pull the object like so over a displacement, delta r. That distance is given to us as 10 meters, and at the end of the problem, the object is over here like so, and it has some speed v. Okay, we're not going to bother calculating the speed in this problem. All that we're interested in doing is calculating the work done by the forces, and then we'll add all of that together to get what is called the net work done. This is just a practice problem, learning how to calculate the work done by forces. A little bit later on, we'll see what the numbers exactly mean. Okay, now in order to calculate the work done by the various forces, we need to know the geometrical relationship between those force vectors and the displacement vector. So off to the side, I'm going to draw the following. I'm going to draw a force diagram. We first of all have the normal force and the force of gravity vertically, just canceling each other out in this horizontal situation, much like we've seen before in other dynamics situations. And then we have the F pull to the right-hand side like so. That's in the same direction as the displacement vector. And then opposing the motion like so is the force of friction, once again labeled as small f. And now we calculate the work done by the various forces. Okay, so first of all, the work done by the normal force. Notice that the work done by the normal force is equal to 0, and the reason for that is because the normal force vector is perpendicular to the displacement vector. Same thing with gravity. No work is done by gravity because the gravitational force vector is perpendicular to the displacement vector. So let's go ahead and write that down as well. Okay, and then we have the other two forces. We have, first of all, F pull, which is in the same direction as the displacement delta R, and the force of friction, which opposes that. So first of all, F pull. Okay, so the work done by F pull is equal then to force times distance, F pull times delta R, because in this case, the two vectors point in the same direction. So all that we do is we take 15 newtons here and then multiply it by 10 meters. This then gives us 150 joules. Okay, now a little bit later on, we'll see exactly what this calculation means, but for now, what I want you to write down in your notes is the following. What is meant by positive work? Okay, we'll answer this question a little bit later on in terms of what is called energy transfer, but for now, I'm going to have you pose this question in your notes for now, and we'll answer it a little bit more specifically later on. The reason for that is because what you're going to begin to learn here at the beginning of this unit is the nuts and bolts mathematically of how to calculate what is called energy transfer. I'm sure that you are familiar, at least qualitatively, with energy transfer from previous science classes. However, what all of those classes skipped over were the mathematical nuts and bolts of how you actually calculate it. It all begins with this definition of work, which we're beginning to take a look at here at the beginning of this unit. So for now, to illustrate the importance then of these work calculations, I'm having us pose this question here in your notes as we go. Same thing for kinetic friction. Okay, I'm going to move to the lower board here. Okay, the work done by friction is equal to negative and then multiplied by the frictional force vector and the displacement vector delta R. The reason for that is because the frictional force vector points in the opposite direction of the displacement vector, hence the negative sign from our mathematical definition from earlier. Okay, now numerically, we're given that the force of friction is 1/4 of the object's weight. So I'm going to write that in like so. And now I'm going to go ahead and plug in the mass of the object as 2 kilograms. multiplied by 9.8 meters per second squared, divided by 4, and then multiplied by 10 meters. This will then give us the work done by friction in terms of joules, and it will be negative. All right, so I'm going to do, let's see, negative 0.25, that's 1/4. Then multiplied by 2 kilograms times 9.8 times 10 meters, and that then gives us negative 49 joules, like so. Okay, with a little bit of practice, doing these work calculations is pretty simple and straightforward, but once again, as of yet, you don't know what these calculations mean. So let's go ahead and put this in your notes. What is meant by negative work? We'll answer that a little bit later on in terms of energy transfer. And then lastly, just as practice, we're going to calculate now what is called the net work done. Its importance we'll get to in the next lecture, but for now we're just doing a practice calculation. The net work done is the work done by all of the individual forces added together. So let me write that out here in words. The net work is equal to the sum of the work done by the individual forces. So in order to calculate the net work, it's called W net, by the way, what we do is we add together the following. First of all, the work done by the normal force, which is 0, plus the work done by gravity, which was 0, plus then the work done by F pull, which was 150 joules, plus then the work done by friction, which was negative 49 joules. Add the numbers together here, and you end up with 101 joules, like so, for the net work done. The last thing that we will note here in this example, prior to moving on, is that in this situation, the object started at rest, and it was speeding up as the situation occurs, like so. So let's note that the object is speeding up. Okay, we'll understand the answers to these questions that we're posing here in your notes for this problem in the next lecture. Let me go ahead and conclude this lecture here.